All right, so before I close the NMR well, does anyone have any questions on that? Okay, so nobody thought of anything. Then we'll go on, and the rest of the time, next hour or so, we'll just work on fluid flow. So basically, I have a couple of exercises in your workshop materials that that just go through how to use all the basic things in the fluid flow. A bunch of it you saw already, so I'm not going to go through a lot of description. I'm more or less going to show you actually just how to use it. So I'm going to start with a new project. Oh wait, I have to. I don't have. I have to share screen yet, right? Am I shared or not shared?
You are already sharing.
I am. Oh, okay. Wish they had a way to tell.
In the bottom, you have the stop sharing or hide a button that says Teams Microsoft is sharing your screen, or at least that's what I see.
Recording is started.
Yeah, you're good. The screen is being shown and it's recording.
All right. So in I'm going to actually do both of these because I think the basic fluid flow shows a bunch of things that we talked about a little bit, but didn't really show how they work. And like, for instance, this exercise will show how to use the water oil contact. And it also shows the effect of PCKR on the both the invasion and the water oil contact. And we didn't see any of those in the morning's exercise. So I'm going to make a new well, and with modeling interval from 1100 to 1200. We will zoom in on that. And then a lot of times it's nice to reduce the reference tracks limits as well. And then we're going to make some petrophysical boundaries at basically we're going to make 3 layers, but we're also going to bound them outside of the modeling interval. So for that, we need to go a little bit outside. So we're going to make some petrophysical boundaries at around 1190. Doesn't have to be exact. And then 1130. And then 1160. And then 1210. Okay. Then we can zoom in again. Okay. Now we're going to set up tracks, and normally if you're going to do a lot of these, you'd want to use a template. I could use a template. Actually, I don't have one set up, but so we'll make a new one. And so what we're going to show is in track 2, we'll show some relevant things for fluid flow. So the well, first we're going to make again a separate petrophysical boundary layer because the fluid flow is going to fill in everything in between these with fluid boundaries. And then we also want to show the water saturation and pore pressure. Make that just a regular line, get blue. And we're going to go from 0 to 1. And let's see. I guess we have it going the other direction in the picture. So we'll have it 1 to 0. And then pore pressure. Okay. And then in track 3, we'll put the formation resistivity. And we'll make it log from 0.1 to 100, so that'd be 3 decades, I think. Yep. And then in 4 to 6, we're going to show some vertical cross-section plots of resistivity, water saturation, and salinity. And so vertical cross-section. So we'll leave that one as resistivity. We'll make it just to 1 meter. And then we can make this logarithmic. And then we'll add water saturation. Also 1 meter. We'll make that 0 to 1. Which sometimes isn't necessarily the best thing for seeing all the contrasting changes, but you can change it later if you want to. And then finally, we'll make the last one be the salinity. Have that go to 1 as well. Okay, and then some of these I'm going to make a little bit smaller just so we don't take up as much space. All right. Actually, the water saturation, I guess I got to keep kind of big. Okay, now we can save this as a new template. And I'm going to call it, go in here and we'll change it to the flow basic. And I can even save it to the user settings. All right, so now that'll be available for us if we make a new well or anything. Now we're going to open the petrophysical calculator. And well, actually, you can do this. So basically, we want to get to the rock class editor. And you can do it from the petrophysical calculator, like described there, but you can also get to it from the multi-well, which is probably the better way to do it now. And we're going to add a new rock class. And we're going to set all the resistivity models to Archies. And I think you actually need to set all of them to Archies. Okay, and then we don't have any other changes to that. So now I also suggest at this point setting, I mean, we already made a template, and you can also save this as an initial starting point for a project if you want, where you have the bed boundary set up and everything. So I'm going to save this as a not sure why it says that. Okay, so we have that init one, and then I'll save this project again and get rid of that and say workshop. That way I just have that clean init one saved. All right, so then we want to open the fluid flow simulation. And we're going to set up just an invasion with 300 overbalance pressure, 4,000 salt for our invading water, and then we're going to set an oil water contact at 1190. So it defaults to the bottom of the interval, which is 1200, but we're going to change it to 1190. And then set the pressure to 3700. And so we'll see what effect this has on our model. And now we'll go into some of the things. We talked about them this morning, but we didn't really do anything with them. We didn't change these things. So in the rock class, we're going to change the layers for 2, 3, and 4. Change the permeabilities to 100, 350. And if you change the first one, I already have 300, so then we get to 50. And then here you can do copy and paste if you want. You just copy that first column and paste it into the second to change it in both directions. The next one says to change the desalt, but we've made that the default now, so you don't have to change that anymore. And then we're going to go into the PCKR Studio and actually do some changes that we didn't do before. So from right here, this will take you directly to the PCKR Studio. And now we're going to change the default rock class to have a PC max of 150 and an E sub P of 9. And so you can see that raises our capillary pressure by a good deal for that class. And then we can switch to the new rock class, which we left as class 1. And this one will change to 80 and leave this at 6. So it's about half the capillary pressure. And then we can go to the palette, and we want to make, you can actually do this in a number of places. We could change could just go here and change this to class 1. And of course here you can see the PCKR curves of the different layers that we have. And the reason that they're different, of course, is because the PCKR system, we save the J function, and then that's what's assigned to the rock class. And so then each layer will have a different PC curve based on its porosity and permeability. Okay, so then if you just want to double check that, we can see in here that indeed if we go to, so this one has rock class up here default, and if we go to layer 3, we have class 1. Okay. So then we want to go to the fluid flow or the fluid flow window again, and we're going to reduce the number of grids. It says to go to advanced, although you can do it here. We'll just look at it in the advanced. We'll leave the R grid blocks the same, but we're going to we just reduced the number of Z grid blocks, and we made it 10. And this is a case that I told you before, that requirements may cause you to have more than 10. So we actually have 25 grid blocks here, and the reason is because we have constraints given by both the petrophysical boundaries and the fluid flow, or the water contact boundary. And so you can see when you initialize with a water contact, you get a line there which will have water all below it, and then it will populate. It will initialize the fluid flow sim with an increasing water as we go up in the formation. And it also starts, because we're going to have the biggest change down by the water oil contact. It automatically does a geometric grid spacing down there, and you can see that that is something that you can adjust here. And so we now so now we're going to save or leave that, and then just to show you the effect that this has, we're going to simulate 0 days, and we're gonna label this 0 day, and then simulate this. And it's very quick because it doesn't actually do anything. Well, it just initializes it basically. And then if you want, we can go to here and we can look at the 0 day, and we can see the pressure and water saturation, and do vertical cross-section plots. And let's see what we get. So here you can see how the water saturation starts off with this 100% water down at the bottom, and then increases based on the capillary pressure as it goes up, and then and similarly the pressure increases as well, or the pore pressure increases as well. And so that's our what's going to be our starting condition, basically. And then I say here, give the option of doing really quick run, but I mean, that's basically, I just put that in there to test, to make sure that you get to see the thing run once. Because some people, if their computers are really slow or they have some problem, it won't run. But I'm just going to actually skip that and run it with the values that we have. So we're going to set the sim now to 1 day, and we're going to run this for 1 day. And it says it takes about 10 minutes. And one thing you should look at right away here, well, there's a couple of things to note here. One is that the step size here, because you see that we have the initial step size being 10 to the minus 15. And here it shows, after 100 steps, we have 10 to the minus 13. Now, it's very easy to, or at least it's common to have some critical parameters set in the Earth model that will cause the sim to kind of get stuck down at 10 to the minus 15, in which case you won't see this changing the way it is here. And so if you see that happen, then you should probably close it and start over and either try to figure out, I mean, because if you try to step up at 10 to the minus 15, it's going to take you forever. And so you should probably stop that and then either figure out what is the problem, which can be fairly difficult sometimes, or you can manually change the minimum step time to be something like 10 to the minus 5. That, of course, will not give you as good of a simulation, but I've seen people use that and get results that were usable for them. It just basically, you can just decide however long you want to wait and calculate, how many time steps based on the speed it's going that it will take to get you to the invasion time that you want. So in this case, it's counting up fine, so we shouldn't have a problem. What else can we say about that? There was something else. Oh, yeah, and the other thing related to that is in the advanced WIM, I told you before, there's that checkbox where you can check save partial sim data. Really, I should probably make that, well, I don't know if that should, I guess it's okay to leave it as default on. But a lot of times, if it looks like you're going to be running a lot of sims that you don't want to keep, you may want to have that set to default off, or set it to off, because there's no point in a lot of times if you're going to be testing a bunch of sims and you don't want to save one that you stop right away, you don't want to keep waiting for it to save or increasing the size of your project just to save those sims. If you do, however, I didn't show you, but well, I guess I still can't show you, but once the sim is done, what you'll see is in any of these places where you have the opportunity to, this is annoying. Any of the places where you have the opportunity to select among the sims that you've run. So normally this drop-down window will show you a list of sims that you've run. Right now we only have one. You also have an X button next to it, and so you can select a sim and delete it from your database or from your Earth model. I mean, I guess it's not really Earth, from the project. And so if you're doing a lot of these and you get too many, you probably want to keep deciding which ones you want to keep and eliminate the rest, because sometimes, especially if you're running a lot of layers or if you're running formation tests, it can make your projects pretty big and things start taking a long time to load or save. So it's just something to keep in mind, but that's another reason why you may want to have that checkbox off that prevents it from saving partial data, unless you really, the only time that that's really useful is if I've had some people who they were running some formation tests that sometimes, can run for days or over a day, and they basically want to run it overnight, and then in the morning decide if they want to stop it and just keep, if it's good enough where they're at, and just stop it there. And so then they can hit stop and it'll save it there, and that way they don't lose a day of data. They can just save the partial run. Okay, so this finished. And so as you can see, this left the window open because we have that checkbox checked, and it shows you, it took 6,700 steps, and it shows you the time steps and the final sim time, almost 1 day. Well, it probably is actually 1 day. And then if you go here now, as we've seen before, you can plot the results. And actually, I'm going to show one. I'm going to show a few different times. So 6 plots. And in this case, I'm not going to worry about the pressure. So we're just going to show the water saturation. So you can see, and actually even at 0.01, we already have some significant invasion. So as I meant for this to show you the initial conditions, but you can still kind of see the initial conditions from the formation zones. But this kind of shows after 0.01 day, and then at the other one I said was 0.2 days, and then after 1 day. So it gives you an idea of how fast the invasion is going. And what you can also see here, and you'll see it also when we import it, is remember that we made this middle petrophysical layer. We had a different PCKR curve, and you can see the effect of that curve here. And so you see how the different layers are affected in both the invasion and in the water saturation profile. So so now what we're going to do is we'll import these results. So now you go to import results. And again, the nice thing about the plot results is you can look at different times and decide which one you want to import. And so, I mean, in this case, we'll import 1 day, but you do have the option to import anything else if you want. I'll calculate, I don't know if we actually need the nuclear for anything. I don't think anything we do is going to use it, so I'm going to not calculate these. And then we'll just import this 1 day. Okay, and now if we go back here, we can see all these things are populated. We're going to do the resistivity separately here. Oh wait, not using a sim, but using a calculator. So these ArcGIS, I'm going to calculate resistivities for water saturation. And again, we don't need the bulk nuclear. Okay, so there you can see that's the formation resistivity. And so now One thing that we want to do is to plot some other resistivities. So because now that we have this invaded, we can see the invaded resistivities. So let's look at, let's see, what do we suggest here? 1, 3, 5, 7, and 9. And so there you can see the effect of from the formation out here to the, I think the black should be number 1. Let me check. Oh, no, the red is 1, which oddly we can't see. Let's make this full screen. Okay, there's the red. And 9. And then, yeah, so we can see go from the first invaded and then the second. Probably these might not be all the best choices. It looks like, oh, I missed 5 somehow. So let's put 5 in there. Should be somewhere in between. Yeah, there's 5. Okay. So we can see how it moves out from the resistivity is changing from the borehole out to the formation. And then over here, let's see the effect of the water saturation. It looks a little bit like, oh, maybe we got the wrong water saturation here. Yeah, so that's looking at the formation, and we actually want to see oops, which one did I pick? This one doesn't matter. We can have this formation. Reset. And then water saturation. Let's see what this looks like in the invaded zone. Yeah. Water saturation. Oh, there we go. No, I think this one. Had a problem with setting the formation value. But yeah, here you can see the water saturation and how it changes from the 100% water down here, and then slowly creeps up, and then there's a slight shift in the middle petrophysical layer, slight discontinuity where it changed and then it continues to rise. So yeah, so this is the resistivity. Probably we should reset the property limits. Yeah, so that gives you a little bit more clarity on the resistivity changes. Okay, so I think Yeah, so that's basically all of the things with the basic invasion that I wanted to show. Just how you can use the PCKR curves to get different and the resistivity and the water oil contact to get these kinds of fluid profiles and resistivity profiles. And then I'm going to make another well, and we'll go on to the exercise, which is the fluid flow advanced formation test. And this one, we're going to start with a new well, and what we can do is just close this well and make a new one. And actually, yeah. In this case, we're just going to have 3 layers again, but we're not going to really do anything to. We're just going to put some shale boundaries on the fluid flow, and so so first we'll set the modeling limits again. And then we'll set some boundaries at 1120 and 1180. And then we're going to go to the actually, we'll open the fluid flow, and because it'll get us to the rock setup faster. So we're going to change the permeability in layer 2 to 10. And then we're going to make these top and bottom layers pure shale. And leave the rest of the stuff as default. And okay, and then now instead of doing invasion here, we're going to turn off the invasion. We're just going to do a formation test on this default formation. And so we're going to hit formation test. Now you can, if you have both of these checked, it'll run the invasion, then the formation test on what you just invaded. A lot of times you may want to consider the formation test to be, you may want to run multiple ones on the same invaded well or not have an invaded well. So you have the option of running it on its own. And so we're going to use this default dual packer. You have 2 default tools, a default dual packer and a default dual probe. And you have the option up here to select either one of those. Well, yeah, you can select either one of those. And then, if you use a new tool, then you can select whatever you want. And then you can change the parameters here. And give it a different name. And actually, if you try to save this without giving it a different name, it forces you to give it. So be sure you give it some name, meaningful name. But instead, we're going to use the default dual packer. And by the way, the point probe, if you happen to select that, it gives you the options of making an oval probe or and having different radii for the center hole and for the rubber boundary. And And then you can also make it standard or focused. But we'll do a dual packer for here. Let's make sure we have a default dual packer. You'll see it starts off centered in the modeling interval. And then we don't want to do any invasion during the test, but we need to set up a schedule. So here you have the options of drawdown, build up, injection, or fall off.
Bruce, quick question. So that invasion that you just showed, where the one you just checked off, is that the same thing as the upper invasion module that it does the invasion first and then do the fluid flow?
Yes. Here?
No, the one at the bottom that you just checked off.
Oh,
yeah,
here?
this one.
No,
So
this has to do with basically if your well is closed or not. So
this is the invasion while you're doing the formation test?
yes.
Okay.
Yeah, so it assumes, I mean, the rest of the, so basically it assumes that your whole well is open except for the part that has the rubber boundary around the tool.
Okay.
And so, if you have that unchecked, then it means that the only place where any transfer between the borehole and the formation is going on is right inside the tool.
Okay. All right. And another question. So if you mentioned that if you do invasion and then you do the formation test, it picks up from your invaded state, right?
Yeah.
So let's say if you have like, does it do it from the last invaded state, or can you pick like what state to start at? Like you can pick the starting point for the formation test. Can you do that?
I mean, if you select it here, it runs it together, so then you don't have any choice.
Okay.
If you run it separately, or I mean, if you don't have this checked, then you can set up the Earth model however you want and run the formation test on that. If you have saved other invasion simulations, you can import whichever one you want and then run the formation test on that. The only difference is if you set up a fluid, if you set up, say, an invaded fluid Earth model, like say after a formation test, you need to select in here the use full Earth model fluids.
Okay. All right. I got what you're saying. All right. Thanks.
Yeah, because otherwise, I mean, otherwise we start off with the formation values or the petrolayer average values.
Okay. Thank you.
So anyway, so typically what we do is a drawdown and a build up, and set this to be 1, and I'm going to change this length of time to hours. So we'll do, actually, what did I, 1 hour for each of these. Okay, so we got 1 barrel per day for 1 hour, and then build up for 1 hour. And then you can see the profile up here. Okay, and so you can set up as many schedules as you want. And then, let's see, and then we'll set this, give this another name like, let's see. Okay, so we'll call this DP hour. Okay. And then, yeah, information values are fine. Okay. Oh, now we need to check the advanced grid. And okay, so now here we have our tool here, and we typically want to have this geometrically expanding around the tool. But it's up to you how many, how fine of resolution you want it. So I'm suggesting here that we change this to 0.5, and then grids 10, and then change this to speed of 0.5. So I'm just trying to get something where there's some finer resolution around the tool, but that we don't have too many grids, because this is an example and I don't want it to take too long. You know, in your own examples, you may want to have more grids or something. It's kind of up to you. I mean, you can see how this works. And so this is, if you zoom in, this is kind of what it looks like. So that shows the grid spacing relative to the tool. And again, right here, especially when you're using geometric expansions, it's hard to predict how many grids you're going to have. So we set the minimum to 10, so it's not going to make any extra. Or I mean, it's not going to make any more than it needs, but we end up with 17 grids, which is not too many. And the azimuthal grid doesn't matter because it's a dual packer. Okay, so we have the grid set up, we have the tool set up, we have the test schedule set up, and those are mainly the things that you need to set up for this. I mean, obviously your earth model, if you want to change those, you may want to play with the mud cake. But otherwise, I think this is all that we have for the exercise. So then I'll simulate this. And this should just take a couple of minutes. And you can kind of chart the progress here. It's going up pretty fast. And you'll see it change over when it changes to the next, yeah, there it started again for the next schedule period.
Another question. Why does it keep saying material balance error in property column?
I think, I mean, I have no idea, but my guess is that maybe that was what it found, and then hopefully it does some correction for that, or it's just telling you that maybe it's telling you that it is correcting for that. I don't know why they, otherwise I don't know why they would have, I mean, or it could be that it's telling you that there is one, but I mean, since it almost always says that, it's hard to imagine that the thing runs with a constant material balance error. So I'm sort of hoping that internally somehow it corrects for it when it finds that. Okay, so that finished. And we can plot history and distribution and cross section if you want of the pressure for change this to hours. So 2 hours, we'll also look at 1 hour. And I should make 4 plots. And so there you can basically see the pressure profile. And then here shows the closer around the borehole at, this is at the end of the drawdown. And then after the buildup, of course, it's equalized. And you can see that effect here. Well, that's actually the distribution, but I guess the pressure we didn't put, we did put 2 times. I'm not sure what this, it only shows, so, oh, this is the history, okay. Oh yeah, here's the other time. So this shows the, at the end of the buildup. Okay, so, and now another thing we can do is, well, you can write that data, whatever you plot, you can write to files if you want to. And it gives you a whole list of files along with a summary that tells you what's in each file. And then the other thing I'm going to do here is we have a few years ago updated our model so that we actually use a full, both the spherical and radial models, the full model rather than just the starting and ending conditions that we used to have. And so you can in here select simulation. When you select the simulation, by default, it'll import all the values from the simulation. If you import your own files, then you'd have to set all this yourself. And this is a common thing where at the beginning it looks kind of funny. It's because the times that are set aren't the exact times that are given by the sim. And so I made a function here, this time adjustment. Basically, it sort of it figures out what the small error is to where the first time should be in order for these functions to look correct. And so
you have a question, by the way, just whenever you have time.
Actually, this is the answer.
Okay.
Oh, I'm not sure what he said, but anyway, so then what you can do is, now I have to say that it's been my experience with doing these sims. It's in many cases, like they don't very well match theoretical sims because I mean, these theoretical models of spherical and radial flow have, you know, a dozen assumptions for them to be able to analytically calculate it, or even create a function that they can numerically calculate, which I guess is what we're doing here. But a lot of times you can get something close. And so then what happens is it shows where this where the sim actually starts off, and then you have a copy of that sim data that you can move. And this is the way that I forget what they call this now, type curve matching. So in type curve matching, what you try to do is you move this, and then you get a pressure and time match based on the distance in pressure and distance in time that you move this, and that pressure and time match determine the properties. And so, well, the pressure and time match in order to, along with the curve that you match, determines the properties. So we can see that it doesn't look like any of the radial ones are really going to fit this very well. So what we can do is we can switch over to the spherical, and also here, I mean, you have a lot of there's these CD E2S values, which for the spherical is a little bit less meaningful, but still useful. But we're clearly have very low CD E2S value, and so we need to try some smaller ones. So you can manually change some of these. In fact, you can add as many curves as you want. It'll calculate a CD E2S curve based on whatever you put in, or you can change any of these if you want. So I can make one that's 10, or I can make one that's 1. Still looks like we're not quite there. Let's try, oops. I think I deleted that one. Let's try 0.1. Okay, now it's starting to look closer. Okay, so you can see that if I put a 0.1 in there, it's getting pretty close there. Now there's also this other curve, and this other curve is based on, it's calculated from the parameters that are in this table, and those can be updated by this auto fit function. And so you could try to set like a different value here. Let's see, we have a very small CD to S And so we can make this like 0.1. So that looks kind of funny. All right, so you can kind of get this close. You can do it manually. Now, I'll try to fit it. I have to say that it doesn't always fit perfectly, or sometimes it gets stuck, but a lot of times we can get a reasonable fit. So you can see the cost function in this case. Okay, still going down. It's having a little bit of trouble. Sometimes it might be stuck in a local minimum here. So, oh, yeah, that one didn't work out too well. Not sure why. Let's try it. You can try it again sometimes. Okay, I have to say I'm not, yeah, when I tested this, it actually found a fit pretty close to this one, but I'm not sure why that's not working in this case. Do 0.5. Let's try this again. Well, it looks like it's just going to stick with that solution. Oh, you know what? I could try maybe increasing the, I might have cut off too much. Maybe this will help. That looks like it makes it worse. Okay, well, anyway, you can see that in this case, it seems like we did better by hand. But in many cases, the auto fit will get something pretty close. And so, and then once you have that, I mean, there's different parameters here. Some of them it says that they're required. Other ones you can set, and based on what you set, it will calculate the unset values over here. So like, you know, the mobility value, the productivity index, and so forth. And in this case, it assumes that, you know, like the permeability. But yeah, if you wanted to calculate the permeability, I think you could, let's see, viscosity, maybe, I'm not sure. I forget which ones. There's a number of dependent properties, and you have to have a certain number of them filled, and it will only calculate the ones that it can based on what you have. Well, let's see what happens if we don't give that a value. Oh, so there it calculates, it does calculate a value, but anyway, so that's kind of what we have there. You can also
I believe it's calculating either the permeability or the viscosity. So when you did not give it permeability, it actually took viscosity be the same as your input, and
Okay.
was calculating mobility based off of your match. So permeability or viscosity comes from there.
Okay. yeah, so that's basically what we have. I mean, the only other thing, I mean, I do go in here and show the 3D, but it basically runs the same as the 2D. It's just a single phase. I'm not sure if you guys want to hang around for that or not. I don't think I have anything really new in it. It's the only, well, I guess the only new thing is that it shows a 3D plotting result. So you can see the, I mean, if you look in the, if you look in the exercise, you can see the graph where it shows you the 3D plot. I don't know, does anybody want me to go through that, or maybe, you know, if I do, maybe you'll get a better fit. I don't know. Depends how long you want to hang around.
Yeah, we've been going for a while, but yeah, if you could do it, I think it would be interesting.
Okay. All right.
Or,
I'll go ahead.
or not too time consuming.
Yeah, let me see. Where did I go? Here we go. All right. So, okay. So if I want, we can change this to 3D single phase. And then we'll change the permeability in the center to 50. And let's see, change this to a new two-hole point probe, and we'll make it 0.75. Give it a new name. And by the way, when you make one of these, they are saved in here. So it's saved in your project. And so, you know, I can go back, dual hacker, go back to the point probe that I created. And I think we can leave the schedule the same. We just have to change the, now hopefully, sometimes have, okay, so something, this is, yeah, it looks like we may have a problem with, I'm not sure why it is, but sometimes when I switch to this tool, I have a problem with my azimuthal setup, and it's weird because if I reload it, it seems to work. But anyway, I'll try it a couple of times and see if it works. So we have the geometrically expanding. So we want to the vertical grid. We'll change it to minimum 10 and speed of 6. Okay, so we got 41, and this one will change to speed of 2. Yeah, so for some reason, I don't know what is causing this. It's a weird bug that's not consistent. And sometimes it works and sometimes it doesn't. I think I'm going to save this and reopen it. So I'm going to save this as PP. And I'm going to reopen this and see if it works then. There we go. Oh, maybe it won't work. Let's see. Nope. I think I had found a trick at one point to get this to work. Maybe if I go back to the change to the other dual packer. Oh, I really got it. Okay. Well, it looks like it might work. All right, so we can try that. It's not the best angular grid, but I'm having problems with that lately for some reason. Okay, so now we can simulate this. And notice that this changed to fluids water only because the 3D is a single phase, so it's just water. And then this shouldn't take very long, I don't think. And then we'll plot again at the 1 hour and 2 hours, and we can see some of the, okay, so we'll open up the plots again. And get the pressure. This time we have also a face cross section, which isn't very interesting, but the top view is kind of interesting. So we'll say 6 plots and plot it. Oh, somehow it's not using the actual grid that it showed me. It's going back to that weird grid. Okay, so pressure at 1 hour. Right, we can still see something. Well, it's not as impressive as my picture. Of course, it might be, maybe I should turn off the color limits and try that. And I'm just trying to zoom in and see if the yeah, so there's not, I mean, as I said, usually you can get a better azimuthal grid, but you can still see some of the effect of that. You have the main pressure change around the tool at the end of the drawdown, and similarly in the if you look at the cross section, and you won't really see much of anything in the other direction. Or at the, that is to say at 2 hours. And then finally, hopefully we can see if this matches something better than the other one did. I don't know what effect that weird grid will have on it. Let's see, we already have spherical. Oh, that's DP still. Hey, what's going on? There we go. Oh, 3D, okay. Yeah, and we'll probably get rid of some of this long time stuff and have a look at something around here. So let's just have a quick check what the, actually we can get rid of probably this one. Let's have a quick check what the auto fit does. Well, it's getting a better cost function anyway. But maybe it's stalled. No, it's still going down. Whoa. All right, so let's see if we uncheck that. So you can see it's actually, you can zoom in on this. It's actually not a bad fit. Didn't catch this kink. I mean, the kink is a little funny shaped, but otherwise, I mean, it's a pretty good fit at CD to S of 3.5 and 0S, which we didn't set any skin factor. So, okay, so anyway, that's how the fit's supposed to work. Yeah, I don't know now, unfortunately. Viscosity, I don't know how much. I'm curious what happens. You're saying if we turn this off, so it calculates 36 instead of 50. Maybe the viscosity is a little bit off. I'm not sure which direction that would go. That makes it worse. Can you have a higher viscosity? Right. You get a really high viscosity. It's too high. Yeah, so, I mean, I don't know. Are there fluids with viscosities of 1.4? Anyway, so that seems to be a much closer fit. So that's, I think that's covers most of what we have available for the testing. Does anybody have any other questions on that?
Bruce, if you're done with whatever you had on schedule, can I request something like a quick look into a few options over here with the formation test?
Yeah.
So on the formation test, if you go into the tool and instead of the standard probe, I mean it's point probe only, but instead of the standard probe, if you choose focused, I had a few questions over there. So for the focus probe, if we go into the schedule, the flow schedule. Yeah, once you apply it and you go into the flow schedule.
Is that a little trouble with the grid on that one? Let's see what could. be that this is too small between R1 and R2, or R2 and R3. Let's see if that.
We can go back to a 2D simulation. That'll be easier.
To what?
I said we can go back to a 2D simulation. That'll be easier.
I'm sorry, I can't hear.
I said if we can go back to a 2D simulation, if that'll be easier.
Oh, that might. Yeah, let's try that. Try making this smaller. Doesn't mean it will necessarily work, but let's see if it. Oh, okay, that actually works okay. All right, so now you're saying in the formation test schedule. And you're you're saying the guard schedule you have a question on, or the
I was having some trouble where it was showing me the guard schedule, and I was wondering if I could put in like I wanted two schedules to show up. Maybe something wrong at my end. But yeah, we can go with say one on guard and 0.5 on wait, what? So yeah, we can do 1 and 0.5.
Okay, wait, you want the guard schedule all drawdown, or you have to tell me more specifically?
Yeah, guard drawdown build up the same way, just like the
okay.
flow schedule. So it'll be 1 0 or 1.50, say 1.50.
Okay. Like that?
Yeah. And now when we simulate it, we'll get pressure, guard pressure.
I think your guard probe is low flow. There seems some problem for the guard, the drawdown, the method.
Oh, no flow. Okay. Flow rate fixed.
Yeah. Thanks.
Okay. I don't know why the default should have been set. Okay. And yeah, I don't. Okay. Let's see. Let's see. Okay.
How long did you leave that simulation to go, by the way?
Well, it's, I think we have it set for,
2 hours?
it's 2 hours, yeah.
And
I mean.
I don't think that's gonna finish.
No, it's gonna let it go for a couple minutes, and if we stop it, it'll save the data.
Okay.
But we might be able to see some effect.
Yeah, we don't have to finish the whole thing. I mean, even if we see partial stuff, that will give me an idea on plotting it.
So let's see, we're at 10 to the minus 10 days. I mean, it's only been 2 minutes, but we'll let it go to 3 and then see where we're at. Another. I'm actually kind of surprised it's running.
Why is that?
Usually if you get a very complicated grid with small grid spacing, especially in addition 3D, a lot of times the thing will kind of get stuck. There's some constraints on the system and it doesn't allow for the grid to change, and so.
Oh wait, it's 3D. I thought we switched to 2D.
Oh, well, the 2D, if you use a point probe, switches to 3D because it has to. I thought you still wanted to use point probe.
Yeah. I wanted to use point probe. But why can't you use 2D in Point Pro?
Because it's inherently
I know,
3D. You have
I know it will do vertical flow. It has to because Point Pro would have a dominant spherical flow, and but it can still do vertical and radial, can it? Or no?
vertical and radial. I mean, it's a spherical flow. I guess if it was perfectly spherical,
You still
could
need the
probably,
azimuth.
I mean, in principle, if you knew that you had perfectly spherical symmetry, you could write your. I mean, you could probably adjust your functions to take into account that symmetry, and then have one less parameter. I mean, just because if it's perfectly spherically symmetric, there should be a way around having to calculate in 3D. But in this case, I mean, I don't think we have anything that assumes perfect, because you have both the layer boundaries and you have the well bore. I mean, and the borehole. So, and also you have variations vertically. So I don't know. I mean, it's definitely not spherical, I don't think.
So with 3D, I thought it did not do. It was just single phase, or in this case, it can do. With Point Pro, it can do multiple phases.
This one can do multiple phases.
Okay.
This is not. There's two 3Ds. There's the 3D single phase, and then there's the what is the old 2D sim, which runs multi-phase, but if you use a point probe, it is 3D.
Okay.
It's just a lot. I mean, I really reduced the grid to try to make it so it would run at a reasonable speed. And I mean, I have to say, I don't know if I've ever seen the focus probe run before. But anyway, it seems to be it's actually getting pretty high up. I mean,
Yeah.
I guess it's probably
I mean,
where we could stop it if we want, but
yeah, for Focus Pro, it's not running so bad.
yeah, I mean, usually, I mean, 3D, the 3D formation tests, sometimes, I mean, I've seen it take days and, it can be really slow.
Is the simulation support multi-process or multi-threads?
Is it
Or
what?
only use one CPU core?
Oh, it only uses one. Yeah, no, it's yeah. This one was not written to be parallel.
Okay.
Yeah, I'm not even. I mean, I know there's people on the campus that run parallel, although it's not quite clear how you do that. I mean, in what sense you can parallelize the whole. I mean, I haven't tried to look into it very deeply, so I'm not sure but it's definitely not obvious to me to start off with how you parallelize this kind of a calculation, because everything's connected and you have multiple phases, and every step a bunch of things have to be calculated, and it's not clear how to divide up the tasks.
I used to use it dual simulation. It takes more than 4 days. And actually, I found it just use one core, and I reported this problem to you. I think just 0 months ago.
Which code is that?
I say one of my simulation takes more than 4 days.
It was what kind of a simulation?
Just for the formation testing, yeah. It takes 4 days to finish.
Yeah, I mean, I've seen that. I'm kind of surprised it finished if it took that long. But was it counting up or did it? I mean, the thing is, when you start to get these 3D grids that are really, that have a lot of different size gridding and stuff like that, I feel like it gets unstable quite easily. And so if it's unstable, then you end up not getting a good change in the time step. So but this is
actually, I think the grid is also too sparse for the simulation. Usually, we need to use a much denser machine for the small probe, right?
a denser formation.
Or denser machine, grids for the probe, near the probe, right?
Oh, near the probe, yeah, more refined.
Because
grid.
the probe is too small compared to the wearable. So
Yeah, that's the problem. And so I mean, and you have to have grids that are the size of the probe at the maximum or maximum. Anyway, you can't have them bigger than the probe around the probe. Otherwise, there's no point in having a small probe. So yeah, you're kind of limited. So, I just realized that this is the first step, but maybe what we can do is, this is at 10 to the minus 2. I think we're going to, I forget what 1 hour is. It's at, should be 0.05 or something. So we can probably get to the end of the, if we get to the end of the drawdown, and then just let the buildup start, and then we can stop it there. Oh, but it's actually, see now I can see the time step is oscillating now. So it's not counting up anymore. It's staying in the 10 to the minus 5s and just oscillating.
Yeah. I mean, if you want, you can stop it and you can just plot the partial results.
Okay, let's see what this looks like. I hope I didn't uncheck that. Oh no, it's writing it out. Okay. All right, let's see what the plot looks like first. Yeah, it's off.
So when it says pressure, what pressure is this?
I think it's the pore pressure.
And I mean, is there a way to plot the pressure at the probe phase? Because we have two probes over here, right? I mean, the probe, which is the concentric, the center probe, and then the guard probe.
Oh, yeah, I mean, you can, by selecting, because you can select different depths. So let me see. I don't know if this, so here's the, it's interesting that I don't see very much difference. I mean, so this is kind of the pressure profile at the probe, and you can see this is the center. And then for some reason, I would have expected to see it darker at the, unless, see it, T equals 1 hour. I mean, we can try an earlier time. I don't know if it somehow had already started. No, it couldn't have started equilibrating. Yeah, I don't know. We can, I mean, it doesn't, I don't see specifically the guard probe here.
I guess we, well, I mean, that would require some playing with some of the gridding near the probe. If we do
Yeah, there
probe,
should be.
If we do probe face cross section, will it show something?
Let's see. I think it's this one. So that should be the cross section.
That's the cross section one, right? And then the right one is for the other, I believe.
I mean, we only have one probe. It just has a guard and a. So there should be a guard around this. If we look at the.
Why do we have 2 plots then?
Oh, because I had 2 times.
Oh, okay.
Yeah, I mean, if we look at the probe, you know, it should look like this. I mean, and it seems like, I'm not sure exactly why there would be much. I mean, we have, the only thing I can think of is that maybe because if it's a total flow in the guard probe of 1.5 and the total area because of the circumference is significantly different, maybe the local flow is less. And so it doesn't show, I mean, basically here you have the entire 1 barrel per day flow going through this tiny half-inch radius hole, whereas here you have a circle that's like 1.5 to 2 inches in diameter or in radius. So actually, like 5 inches in diameter or something, with the same amount going through it. So that might be why.
You don't really see the focus effect. Is that what you're saying?
Yeah, I think that might be why we don't see here, because I mean
So the plot that you're showing right now, it says both at t equals to 1 hour.
Well, that's because we stopped at before. We stopped a little before 1 hour, and so
Okay,
what I
so
asked for was.
It's plotting both at 1 hour, not 1 and 2. Okay.
Yeah, because we don't have any. It just gets the closest point it can, which is,
Okay. I get what you're saying. All right. No, thank you for this. I'll play with this some more. I was getting some errors, but I don't see you getting them, so I'll try it again.
I mean, one option you could think of is actually having no flow in the center and then seeing if you see a circle around. But the other problem might be that the gridding, because we had to have such fine gridding or such coarse gridding, that if you look at the grid, I mean, it looks okay, but I mean, it's actually not bad. But I mean, you can imagine right here, if, it's blocked. And so if you actually do the calculation and the grid looks like this, it's hard to say what it's actually going to, look like. You kind of have, 3 lines instead of a circle there.
Mhm.
But this does give you an idea of here you have 1 grid versus 12, taking the same amount, almost the same amount of fluid.
For a grid like this, I think the area of the probe should not be the same as the actual one, right? Because the area of the square should be not the same as the area of the circle probe.
The
I mean, there
areas,
So you're saying that
the area is are different.
oh, the areas.
yeah, the areas are different because of course the radii are different.
Yeah. So the simulation result should be not completely the same with the practical one.
I guess it'll require some playing with the flow rates and seeing if the different flow rates
Yeah.
can produce that kind of a focused effect because of the difference in areas. I mean, you would expect to see the effect of difference in areas. That's why the focus flow came into existence, because it would have that focusing effect on the flow geometry. I just wanted to see if we can see that focused effect on the simulation.
Well, I mean, I think you are seeing something, because if you, in that plot, if you only had the center hole, all you would see is like one small blue dot,
That's true.
and you wouldn't see it because the shading was really smooth going out from the center out to, the.
Yes.
So it actually covered this whole area. You could see that there was an inflow, but you just didn't see these. You didn't clearly see these lines as having dark values.
Yeah.
Yeah, you could try different flow rates. I have to warn you that I mean, there's certain conditions on in fluid flow that conditions on the rate of flow versus the size of a grid that sort of limit the size of the grid that you can have versus the time step. And so basically, if you start getting the grids too small, it'll have to keep reducing the time step smaller and smaller. And so it will take a lot longer. And you may want to start with a smaller total region than we had here. Make your modeling interval small. I mean, clearly this isn't having very much effect on, the surrounding area. So if you could run for a short time on a smaller, try to minimize the grid to be just around the tool. However, keep in mind that you have to be a little bit careful about, some people try to reduce the radial extent, like the external radius. And I mean, you'll run into problems if you get too much flow that the pressure gradient reaches the boundary. I think that'll no longer satisfy the boundary conditions. So.
All right. Yeah, I'll be careful of that. I mean, I can reduce the area exposed to the flow, or the area that we're taking into consideration. But of course, I don't want to reduce it too much where we start, like you said, where we start seeing the effects of the boundary.
And also, now, if you want to get, you can add, we didn't do this because I wanted to keep it as small a grid as possible, but you can add more grids to the tool if you want to get, a better shaped tool. I mean, I don't know exactly minimum number of grids, like if you had determined vertical grid, I don't know if you had 10. Well, that still doesn't, actually, I think that would fill that out. I don't know, maybe my algorithm isn't very good. That's not, I would have expected it to maybe put let's try 20. I don't think you'd want to do this because the number of grids
Or
that this
take-
would add to.
It will take
Huh.
forever.
Yeah, and also it doesn't seem to be improving the. I think there's a. I've never actually tried using really big grids because it seemed impractical, but I do think if you use a grid or this many grids, you should see a more sphere or a more circular probe. So that might need some work, I guess. If anyway,
Good to know. I'll try out a few things. If I have any issues, I'll reach out.
okay.
Thank you, Bruce. Appreciate that. Thank you.
Yeah,
Sorry
sure.
I kept everyone held up. Sorry about that.
Well, anyone wanted to leave, they could leave. So, all right.